We're going to get to this next question here. But when again, before leaving this question, emphasize that the purpose of all this is to, in the end, estimate this value or show that this value, is there any evidence that this value, this parameter, is correct or not correct? That's how we'll use this information later. What I'd like to do now is look at questions that are a little bit maybe unusual to make you understand that it's the question that allows us to be in the situation where we need to do a sampling distribution. Here, a lot of the information was already provided for us. I mean, we're told what P was. In other questions, we have to maybe look at what we have and find that information. So let's look at this question, and we have seen this in the other scenario for the sampling distribution of the mean. It's the same scenario. A person is paid once a month for working in a company. Suppose that the person gets paid randomly according to the table shown right here, where the random variable is the amount of the monthly paycheck. And we have this standard deviation of 328 and a mean of 3420. So this is the same scenario as before. But this time, again, I want to reemphasize that the distribution is discrete. And we've talked about this, but let's get to the question. So the scenario before, we used this to find a single value and then talk about the average of certain paychecks. But now we're not, the question is different. So the question is what drives the distribution. The sampling distribution is driven by the question. Suppose that you sample 90 paychecks at random. Okay, so again, we know that N is 90. What is the probability that the 24 or more of the paychecks worth are greater than 3,600? Okay, so there's a lot to take in. What's the probability that the 24 or more? So out of 90, 24 or more are what? Their paychecks are worth is greater than 3,600. So this is the criteria. I'm still counting. Notice, I want 24 or more out of the 90. 24 or more is a count. And this is the criteria. What is it that I want those paychecks, 24 paychecks to be 3,600 or more? So this is a sampling distribution of proportions question. Because every time, what's going to happen? What does my data look like? My data looks like a bunch of paychecks. It could be 3124. It could be 3560. The next page is 3560, and so on. Maybe 4100, back to 3124, back to 3124, and so on. And we're going to do this 90 times. But what am I doing with these? Of these 90 checks, I'm going to determine if it's success or failure. Success is if paycheck is 3,600 or more. So this would be a failure. This would be a failure. This would be a failure. Success, failure, failure, and so on. So I'm turning my numerical data into successes and failure using this criteria. And I'm looking for 24 successes. So the p-hat value that I'm gunning for is 24 out of 90. If that's the case, what is P? P is this. P is the probability that a single paycheck is greater than $3,600. What's the chance of that? Well, let's see. We can only get 3,550, 3,900, 4,100. This is a failure, failure, success, success. So the only way we're going to meet that criteria is if this paycheck shows up and this paycheck shows up. What's the chance of that? Well, 15% plus 5%, total 20%. So the probability of success is 20%. This is now the mean of the distribution of p-hat. This is the center. And it will be the center regardless. This center is not dependent on sample size. It is true. What is the center dependent on? Unbiased sampling process. Can I draw a normal distribution above? That's a different question. This will be the center regardless of what shape sits above this thing. If I want to understand something about the shape, I must now deal with the CLT. So the central limit theorem has nothing to do with the center of this. Of course, we will like everything to line up, but this has to do with unbiased sampling process. So even if I don't meet the CLT, this will continue to be the center of this distribution. But can I draw that normal shape above? Well, the only way I can do that is if I meet the criteria. So I take P, again, this is the criteria I must figure out. Do I meet that criteria? I think I might, because let's see, 20% of 90, is that greater than 10? Yes, it is. I mean, 20% of 90 is, that's 10% is 9, so this is 18%. Sorry, 18, not 18%, 18. So that's 8 greater than, yes, look at that. And if that's true, then remember, it's going to be 90 times the probability of failure. If 20% is success, then 80% of the time it's going to be failure. And I don't need to multiply that. I could realize that, yes, it's greater than 10. So this allows me now to draw this above. So unbiased sampling process allows me to put this at the center. This criteria allows me to draw the picture above. How do I know my sampling process is unbiased? Well, remember, we have to kind of read into this. It gets paid randomly. Maybe there's a machine out there using a random number generator. It's already created to pump out these numbers are completely at random, just pretty much like a slot machine in Las Vegas. Where slot machine in Las Vegas, there's certain payouts out. It's computerized. These values are just inputted, and when you press the lever in a slot machine in Las Vegas, all it does is send a signal to a random number generator to produce a certain outcome according to some set table of probabilities. That's all that's happening. The process used to be mechanical, but that has long been done away with. So I meet that criteria. What else do I need? Do I meet the 10% rule? Yes, because remember, if this is being done by a machine, this is same as tossing die. In other words, I'm sampling with replacement. The computer just resets itself. Just because you get 3124, which has the highest chance of occurring, doesn't mean next time this has a greater or less chance of occurring. The computer doesn't care. It will produce according to these numbers. So it's sampling with replacements. None of these probabilities are being affected from sample to sample. So now it's just a matter of going through the motions of the calculation. Let's find the z-score. What are we after, by the way? I already forgot. 24 or more. 24. What's this value here? What is that approximately? Just to get it on the right side of. I'm going to do this on the calculator on the side. Okay, 0.0266. I want 24 or more. In other words, 26.6% or more. 0.2. So somewhere here. 0.266 or more. That's what I'm after. Again, 20% success, 80% failure. Notice these two numbers have to add up to 1 divided by 90. Some values here. Sample size is now 90. Probability of success is 20%. Probability of failure is 80%. This value here is 20%. And my measurement, I'm going to just enter it exactly. I'm going to hit the little fraction button and just type it at 24 divided by 90. And there we go. Notice now this is getting in somewhere in between the usual and the unusual. We're now moving in a direction of towards the unusual. How unusual is it? Let's find out. So 24 p-hat value 2490 or greater is equivalent to a z-score of 1.5811 or greater. I'm grabbing 4 should be fine. I'm going to grab 2 more. I just want to make sure. And of course, I got to go in the right direction. So I got to press here and also change the sign to the right one. 1.58114. Okay, that's good. And I get about 5%. And I'm not too surprised. It's almost 6%. So now this is now the beginning of the realm of from the usual to the unusual. This is right at this edge right now. That's how you would work it. What the lesson here is that I had to find my value of P, understand what was happening, and then find the pieces that needed to be. But notice I had to get that value from this information. And also the question drives the sampling distribution proportion. It's the question. If I see this, I can't assume that I know what I'm about to do. I have to read the question. What is the question? And then that puts me in the right situation.